first level of organization in biology, as you recall, is the chemical level. So in order for you to have an understanding of the chemical reactions and the chemical makeup of biological organisms, we first need to go through some basic chemistry. So let's start with the simplest matter. So remember, matter takes up space and has mass. And matter is composed of elements, and the smallest piece of an element is an atom. So I'm sure you remember your periodic table, the elements, carbon, oxygen, hydrogen, iron. Those were your elements, and they were made of atoms. And what made each element specific or unique was the number of protons. That's the one thing you cannot change in an element and still have the same element. In other words, if I have carbon, carbon always has 6 protons. I can change the number of neutrons in carbon. I can change the number of electrons in carbon. I will still have carbon. But if I change the number of protons, it won't be carbon anymore. It will be a different element. So that's the one thing that makes an element unique. Next, make sure you know the parts of the atom and their charges. I'm pretty sure everybody remembers this. Protons and neutrons are found in the nucleus. Protons are positive. Neutrons are neutral. They don't have a charge. And they compose the nucleus. There's no membrane around it or anything. They actually create a nucleus. And then the electrons with a negative charge are found around the nucleus in what we call the electron cloud. Now, the only electrons we're really going to talk about in here are going to be the valence electrons, which are the ones in the outermost shell. Those are the ones that will determine its chemical behavior. In other words, how an atom reacts with others. If you're asked about the reactivity of an atom with other atoms, the thing that's going to determine that is going to be the electrons, the valence electrons specifically. And that's because atoms want to have 8, with the exception of hydrogen and helium because they're in the first row of the table. All other atoms typically want to have a full outer shell, and that's going to be 8 electrons. So why are we talking about atoms in here in biology? Well, it turns out that atoms are obviously what compose us, and there are 4 main ones. 99% of our body is made of really just 4 elements: carbon, hydrogen, oxygen, nitrogen. And you can remember it by remembering CHON. Sometimes they add phosphorus and sulfur to this. So you could say that the 6 elements that we are composed of would be CHOMPs: carbon, hydrogen, oxygen, nitrogen, phosphorus, sulfur. Why those? Because remember, what are we mostly made of? Water. We're like 60 to 70% water. That's hydrogen and oxygen right there. And then carbohydrates, proteins, lipids, and nucleic acids, DNA and RNA, contain also hydrogen and oxygen, but carbon, nitrogen, phosphorus, and sulfur. So these are the compounds or the elements that compose us. Now, that doesn't mean we don't need other elements. We do. They're called trace elements, and these are the elements that we need in small quantities. Without them, we can get really sick. This is like your vitamins and your minerals and things like that. And I gave the example here, and you don't have to memorize it, of iodine. Iodine, you only need 150 micrograms, if you're not familiar with that symbol, which you actually need to be. But a microgram is 1,000th of a milligram. It's basically, so this we're talking about just the tiniest amount that we need. But without iodine, if you had an iodine deficiency, you actually end up with thyroid problems. In this country, we really don't see it. I have a picture here of somebody with a goiter. You can see how their neck is swollen. Their thyroid gland is swollen up. And there's other reasons somebody could have a goiter. But in this country, you're not going to see people that have goiters because of iodine deficiency. And that's because in this country, they actually put iodine in salt. So when you buy salt, you're technically getting iodine through that. And so you're probably getting all the iodine you need just from your daily diet. But without it, you can get very sick. And this is true in not just us, but in plants and animals as well. I listed selenium here. A selenium deficiency in like cattle and horses can cause nerve problems and muscle spasms and all kinds of things. And so if they're not getting it from the grass that they're eating, they can actually get really sick. And chromium is another one. So you do need other elements to be healthy. But CHON or CHOMPs would be the way to remember the macro elements, the ones that you need in large quantities. Okay. Going back to our chemistry review, so the atomic number is the number of protons that an atom has. It's written in the bottom left. And the mass number is the number of protons plus neutrons added together, and it's written as a superscript in the top left. Now, there's also what's called atomic mass. So they both have mass, so be careful. Mass number is a whole number. Atomic mass is a decimal. Atomic mass is the average of all the isotopes in nature that exist of an atom. In other words, all the different atoms with different numbers of neutrons. So, for example, carbon, there's a carbon 12 that's written like this. There's a carbon 13, and there's a carbon 14. These are all what we call isotopes, which is going to come up on the next slide, of carbon. Now, they all have 6 protons, but carbon 12 has 6 neutrons, carbon 13 has 7, and carbon 14 has 8. The atomic mass on the periodic table, if you look up carbon, you'd see the C here, and then you'd see a 6, that's its atomic number, and then you would see down here a decimal. And that is the atomic mass. It's the average of all the carbon isotopes based on how common they are in nature. Since the atomic mass of carbon is 12.011, we can assume carbon 12 makes up most of the carbon in nature. That these two exist, but they exist in very, very small amounts. So the atomic mass is a decimal. You wouldn't actually find a single carbon atom that had a mass of 12.011 AMU, just like the average number of students in a class might be 30.5, but you wouldn't go into somebody's classroom and find 30.5 students. You would find either 30 or 32 or 28. You'd find a whole number. And the same is true here. So the mass number is a whole number. The atomic mass is an average of all the isotopes in nature, all the different whole numbers, but based on how common they are. Usually the way we write our symbols is what's called A to Z notation. You should know how to write it and also how to read it. So I have here on the left, you can see carbon as my example, the atomic number in the bottom left, the mass number in the upper left, and then if you wanted to know how many neutrons this had, you could subtract 12 minus 6, and there would be 6 neutrons, because remember, this 12 is the protons plus the neutrons, and this 6 is the number of protons. And I have a practice one on the next slide. So for this, I have 2 elements off the periodic table, and notice these are actually atomic masses, but what I stated here is to write the notation, and let's assume that we're using magnesium-24, meaning the magnesium isotope that specifically has a mass number of 24, and chlorine-35. So we're using the chlorine that has a mass number of 35, because those are actually the most common isotopes, because if we round these, that would basically tell I'm getting these whole numbers. But these, remember, are atomic masses at the bottom. All right, so let's start with the magnesium. So the magnesium has 12 protons. That's its atomic number. That goes in the bottom left. And then I said to use magnesium-24, the one with a mass number of 24. So the 24 would go in the top left. The number of protons would be 12. The number of neutrons would be, remember, that's going to be your 24 minus 12, which is 12. And technically, the number of electrons, by the way, would also be 12. And the reason why is because the protons and the electrons have to equal each other, or else it would have a charge. And we don't see any kind of charge. They're always neutral in nature. All right, and here's our chlorine. So 17, our atomic number, would go on our bottom left. We're using chlorine-35. So 35, our mass number, would go on the top left. The number of protons would be 17. The number of neutrons would be 18. How do I know that? Because it has to add up to my 35, so subtracting. And technically, although I didn't ask for it, the number of electrons would also be 17 because it's neutral. There's no charge. So that's how you would write these. And I know I'm going through this fairly quickly, but this should be review. All right, isotopes. So isotopes, I've used the word a couple of times previous to this slide, but an isotope is what we call atoms of the same element, but that have different numbers of neutrons. And again, pretty much every element on the periodic table has 2 or 3 isotopes in nature. So I gave the example previously of carbon-12 and carbon-14, and there's also a carbon-13. So carbon-12, carbon-14 would look like this, and then there's also a carbon-13. Why do we care about isotopes in biology? Well, one of the reasons we care about them is specifically the radioactive ones. So whenever there's extra neutrons in the nucleus, it turns out that some isotopes, not all of them, but some, particularly the ones that have a lot of neutrons in the nucleus, are radioactive, which basically means they're unstable. Their nucleus is unstable, and over time they will break down. Why that's useful is because for one thing, they decay, or they break down, it's called decaying, at a specific rate called a half-life. And the half-life differs for each element. So for example, carbon-14 has a half-life of 5,730 years. In other words, we know exactly how fast carbon-14 breaks down. Potassium-40 has a different half-life. And there's also uranium-238. It has a different half-life. They break down at different speeds. The bottom line is we can use this to date fossils. If we dig up a fossil, knowing how quickly these radioactive isotopes break down, we can look at how much of the radioactive isotope is broken down and how much is left, and we can figure out the age of the fossil. And you're not going to have to actually calculate half-life or anything like that. Another thing we use it for, so I mentioned dating fossils because they decay at certain specific rates. But we also use them in medicine as tracers because they are radioactive. They actually give off energy, and so they glow under X-rays. So if we inject somebody with a radioactive isotope, like radioactive iodine, or we can have somebody drink radioactive barium, and then take X-rays and do things like an angiogram or a CAT scan with contrast, things like that, we can actually see parts of their body light up under X-rays. I'll show you a picture on the next slide. And we can also use it in radiation treatment for cancer. Certain isotopes will kill the radiation will kill cancer cells. So there's a lot of reasons why we might use isotopes. This is just showing you what half-life looks like. So you'll notice over time how this is breaking down. This is carbon-14. So after 5,730 years, about half of the carbon-14 in a sample would have decayed into nitrogen. After another 5,730 years, a second half-life, now another half would decay, and you'd only be left with a quarter of your original sample. So if you were to dig up a fossil and it contained about a quarter of the amount of the original sample, and the rest was decayed into nitrogen, you could estimate the age of that fossil as 11,460 years old. And it goes from there. So you can use them to date fossils. Also, here is what an angiogram looks like on the left. So notice how the blood vessels all light up under X-rays.